In this lesson, we're going to be looking at section 2.1, part 2. We're going to be looking at limits, and particularly some techniques for determining the limits algebraically. Okay, and so again, not all of these techniques are always used. You just figure out the situation when they're going to be used, and it is not a complete list. We will be adding some stuff to it later once we learn how to do other things. So here is our basic algebraic limits. The first thing we're going to do when we do have a limit that we need to try to evaluate is we're going to try to do direct substitution. Okay? Always try this technique first. In many functions, the limit as x approaches c of the function is f of c. Okay, so we try this technique first. So let's go ahead and do a couple of those and show you how that's done. So here's a couple of examples for us. So here's the function x squared plus 4. So we know that that's a parabola moved up 4 units. So what happens as x approaches 3? What I want to do and how I want to write it would be simply to take the 3 and substitute it in for x, and then you work that out. So you have 9 plus 4, which is 13. My limit is 13. So if you plug a number in and you get a value, that is the limit. If you plug a number in and you don't get a value, then you have to do other techniques. So even this one right here that's really ugly, let's take a look and see what we have to do. So according to our technique, I can take this, I can try and plug it in, and we have, so here's the key. If I look at this thing closely, I'll notice that, pay attention, don't just do it blindly. At the bottom is going to be 0. So this is a problem, because the bottom of a fraction can never be 0. So this is going to produce something that is not going to be a number. And you can see that obviously right off the bat because of 0 on the bottom. We still want to plug it in to see what kind of things we're getting, because that will then determine how we proceed with this problem. So because I know that the bottom is going to be 0, don't put an equal sign, because it is not equal. Equal implies that it's equal to a value that's of some other value, and this one will have no value. Okay? So you can simply put an arrow, and we plug this in, and we can get a 3 squared, 4 times 3 minus 21, and 9 minus 3 squared. So the top is going to be what? We know the bottom is going to be 0. What is the top going to be? Well, it's going to be a 9 plus a 12 minus a 21, which is also 0. Excuse me, don't put an equal sign. And so we get 0 over 0. Okay? So you don't ever use an equal, you can't see what I'm doing, sorry. Don't use an equal sign if it's not going to produce a number or an expression that we can then use. This is going to be what's called an indeterminate form. Okay? Indeterminate form. 0 over 0 is an indeterminate form. And for this, we have to use a new technique, because we can't have 0 over 0 in this situation. So a new technique has to be applied in here. And in fact, one other technique would be the factoring technique, as you can see right here. Because these are polynomials, I can factor these and see what occurs there. So in the factoring technique, I'm going to just change the way this looks so it isn't equals. Make sure you always write everything out. And now factor the top and the bottom completely. Down here we'll get 3 plus x, 3 minus x, because it's difference of 2 squares. And on top, we're going to get x, 7, and 3, and plus and a minus. And then what we notice here is that these are very close together. They only differ by signs. So we can do a reduction of this. When you see that just all the signs are reversed, then it's just a -1 common factor here. And so I can actually rewrite and bring out a negative from this. And I would get a -1 times x plus 7 times 3 minus x. And then this is still the same on the bottom. and then 3 minus x. And we'll notice that these two values can now be reduced. So then this problem right here becomes the limit as x approaches 3 of a negative x plus 7 divided by 3 plus x. Now can I substitute 3 in? Now can I take this and plug in the 3? 3 plus 7, 3 plus 3, and we get the grand total of a negative 10 over 6, which can then reduce down into a negative 5 over 3. Okay? So let me show you some additional stuff here so you kind of see some added notes that I put in there in case you want to put those in there. So again, just what I told you before, don't put an equal sign here because you can't have it equal to 0 over 0. Okay. Factor and look for common factors that can be reduced. Remember, common factors represent holes in the graph. Okay, so that would be those ones where we had a hole in the graph. Factor it completely. Now I can direct substitute. On an AP exam, free response, if this occurs on there, you can actually stop right there. You do not have to work this out and get a number. Okay, as it was told to me, I'm telling to you, the AP exam, this right here, it's not. They're not testing you on your arithmetic. They just want to know, do you know how to do the limit? So once you start do your direct substitution right here, you don't need to simplify it out. Now for my tests and stuff you do, but I'm just telling you for AP exam. So we're kind of seeing how we want to go about doing AP stuff. So let me go ahead and move this over with another example. Another example with another technique. Here it is still factoring technique, but we have this right here. This problem looks very complicated. We have a complex fraction in here, so we have this fraction minus that over that. Okay. We'll notice that if I try and plug in negative 8 on the bottom, I'm going to get a 0. So this tells me that I'm going to have to do something else. I cannot do direct substitution. So what technique can I use here? And since this is a rational function right here, I can eliminate these internal fractions by multiplying the top and the bottom by the least common denominator of all the fractions in here, which is x plus 6. So we're going to multiply the top by x plus 6 and the bottom by x plus 6, noticing by multiplying by 1. And that will change the way this looks, and maybe we can do something from there. So x approaches negative 8. On top, I'm going to distribute that over. I'll have an x minus 4 times x plus 6. On the bottom, I'll have an x plus 8 times an x plus 6. And so let's clean up the top part in here. Okay, see what we have. Negative 8. And then over here, I'll have x minus 4x, which is going to be a negative 3x. And then negative 4 times 6 is negative 24. And I think you can hopefully see where this is going to go. And so then the top, if I factor the top out, I'm going to get a negative 3 on top, and then an x plus 8, x plus 8 on the bottom, x plus 6. And you'll notice that this common factor will make this drop out, leaving this new expression, which allows me to do direct substitution. So I'll get negative 3 on top. I'll get negative 8 plus 6 on the bottom, which gives me a grand total of 3 over 2. Okay, so these are all the techniques we can use to find these two techniques we can use to find a limit of a function expression. Okay, so what are some other ones I can use? Well, the next one is the rationalization technique. Okay, you can rationalize. So right here I have a radical in here. Notice again, if I plug in 5, I'm going to get 0 on the bottom. Okay, so that's our problem. That's the problem. So what can I do here? Unlike this one, there's no internal fraction. So this one has a radical. So I can rationalize it. Now, normally we rationalize the denominator, getting the radicals out of the bottom. But in this case, what I want to do is I want to change the way this looks. So rationalizing means I can rationalize the numerator or I can rationalize the denominator. And to do that, you just use the same technique. So since the top up here has the radical, think of this as big parentheses like this, I'm going to multiply the top and bottom by the conjugate of that expression. And remember, the conjugate just means I'm going to set it up so it looks like the difference of two squares. So instead of a -3, I'm going to put a +3. And I'll do the same thing on the bottom. And then I multiply this out, getting a new limit function. And bottom, I'm not going to multiply it out. I'm just going to leave it as is. X plus 4 plus 3. Because it's really about the top up here. We're hoping that something's going to come out and we can get rid of this x minus 5. See, because that's the thing that's bothering us on the bottom here. So if I multiply all this out, remember it's the difference of two squares, it becomes this quantity squared, so that's going to be an x plus 4, minus this quantity squared, which is going to be 3 squared. And then you can see clearly that on top it's going to become the expression x minus 5. Thereby removing the x minus 5 on the bottom over here. Sorry, I didn't write enough room. So this expression right here is that. And the x minus 5s will drop out, leaving, as x approaches 5, on top, we're going to have a 1, and on the bottom, we're going to have that long radical expression, which I can then substitute into. So now I can do direct substitution. This will be the square root of 5 plus 4 plus 3, giving us a grand total of 1 over 6. Okay? So here's another technique, and there's multiple techniques for this. I mean, as you look for this one, we'll see we have radicals on the bottom, 2 of them, okay? But if you really work on this and start seeing different things, you'll notice that I could have done a factoring technique for this. I could factor the top, and then I can look at those and factor them again, and maybe I'll show you that here in just a little bit. But if we do this as a rational technique, I need to get rid of those radicals there because, again, if I plug in 5, I'm going to get 0 in the bottom. So I'm going to multiply the top and bottom by the conjugate of this item on the bottom, which means square root of x plus the square root of 5. That's the conjugate. Making it look like the difference of two squares. So let's go ahead and work the top part out, okay, and the bottom part and see what we come up with. So if I multiply this stuff here on the bottom, right, because this is the difference of two squares, I'm going to get the first quantity squared minus the second quantity squared. And then this right here can be factored because this is the difference of two squares. And don't forget we multiplied by this quantity here too. And there it is. There's our ability to reduce that common factor. At this point, I can then substitute in our 5 for direct substitution. We end up here with x plus 5, the square root of x plus the square root of 5. The way you write things is very important. You want to always make sure you write things out properly. So yes, I need to continue this and not just jump to an answer. At this point, I can now do direct substitution. 5 plus 5, the square root of 5, plus the square root of 5. And then simplify all this out and work it out and stuff. And you're going to end up with 20 times the square root of 5. Okay? So, again, here's my full notes over here so you can kind of see that now. Let's go ahead and look at some other techniques. The next technique we're going to look at is the trig techniques. Okay? In the trig techniques, we need to keep in mind a couple of different things. We're going to have to think about some identities. So a lot of our common identities we talked about in pre-calc are going to be in play. I did write a few other ones down so that you would have those also. Here are just some of the identities. This is the Pythagorean identity. And these are some double angle identities. for sine and cosine. I mean, clearly we can do the tangent ones also, but these are the limits really that we focus our attention to. Okay, so a lot of our trig stuff is designed to get into one of these formats right here. So these four right here, you're going to want to memorize. You need to know these. Okay, the limit as x approaches 0 of the sine of x over x is 1, and then the two other variations on it. Notice here it's the same thing but with an a in here, and then our answer becomes a. And then what if I have a sine over a sine of this? Then it becomes that fraction that's in there. Okay, and then cosine has this one right here. So when we do the trig techniques, we're going to be doing things, getting it into using identities to get it to look like something like this, so that we can then use our properties to find the limits of these items. And so here I have a couple of examples we'll look at here in this video. So here's our first one. So what we're trying to do is trying to make this look good. I can't plug in pi over 2. If I do, the cosine of pi over 2, we all remember, is 0. Okay? So we can't plug in pi over 2, can't go direct substitution. And so now I need to then change this. But then I notice that this right here is related to a Pythagorean identity. This right here is equal to the cosine. So 1 minus the sine squared is the cosine squared of theta. And this is a common factor. You know, this is cosine times cosine, so one of them will reduce out. So this becomes simply that right there. And then as I do direct substitution, we now know that this answer is going to be 0. Okay, here is another one right here. And again, we want to learn some of our identities that will make our life a little bit easier. But first things first is, what happens if I do direct substitution? Because you always check direct substitution first, and I always check it in the bottom first. Because if the bottom is not 0, then I'll check it in the top. But if the bottom is 0, then I know I have to do some other technique. So I'm not doing the trig technique just because there's trig here. I'm doing the trig technique after I've checked direct substitution. And I notice that the bottom will produce a 0. The cosine of pi over 4 and the sine of pi over 4 are the exact same number, so this will reduce become a 0. Which means I need to do a new, change the way this looks using an identity. And the top one right here, is that one. And so it's a double angle identity. And so I can then just use that and change this directly to the cosine of 2 theta over this. And then I can say, okay, well, since that's a double angle, cosine's unique and it has what? It has multiple forms of the same identity. And so then we can use that one because that's similar to what's on the bottom. I could have gone directly there, but I wanted to go through here to show you it was another form of the double angle. Pi over 4. This is now going to be the cosine squared of theta minus the sine squared of theta over this. And this is just the difference of 2 squares, so we're going to factor that. And so I'll have the cosine of theta plus the sine of theta, the cosine of theta minus the sine of theta over this. And you can see that these will reduce out, leaving this limit as an equivalent limit. And now I can do direct substitution. As I plug this in, I get the cosine of pi over 4 plus the sine of pi over 4. And we know that this is the square root of 2 over 2 and the square root of 2 over 2, which means I have the square root of 2. That's my final answer. Okay. Another technique, piecewise. Okay. Let me show you this real quick so you can see the. So there's the same ones we were just doing. Piecewise function. If x approaches whatever the separation point, take the limit from the left and from the right. The limit exists if they agree. Okay, so in our piecewise, we want to take the limit from the left and the right if necessary. Remember, if x is approaching the separation point. So what is the separation point? So in this problem over here, the separation point is, you can see this number right here, which is -2. Okay, I'm approaching -2. That's the separation point. Okay, you can draw a little sketch of this if it helps you out, but you don't necessarily need to. We need to take the limit as x approaches -2 from the left of that function, and we need to take the limit as x approaches -2 from the right of the same function. So what you want to do is visualize and think about, okay, which piece is on the left of -2? Well, left means less than, so this is the piece they're talking about. So you can then rewrite this with the piece that you're looking at in here of 3x plus 3. And we try this out here. Can I do direct substitution? Yes, I can. So this is going to be 3 times -2 plus 3, and I get the number -3. Now I'm going to approach -2 from the right, so that means I'm going to be using, the right means greater than -2. That means I'm using this piece now. So this is the limit as x approaches -2 from the right of x squared minus x minus 9. And then can I do direct substitution? The answer is yes. Minus -2 minus 9. And you work this out and you get -3. And since they both agree, okay, since the limit as x approaches -2 from the left of h of x equals the limit as x approaches -2 from the right of h of x, then, and that's equal to -3, then I know that the limit as x approaches -2 of this function must also be -3. And so that would be how you would write your answer. Okay? So that's how you deal with piecewise functions. The last one here that we're going to look at is we're going to look at the squeeze theorem. This one's sometimes they'll have you guys talk about this one and work with this one, but keep in mind that there's certain techniques for solving these things out, and I'm going to show you a couple of those things here. But don't panic on this one. All this is basically saying, sometimes it's called the sandwich theorem. What it's basically telling you is this: I have a function g that is always between f of x and h of x. So two other functions. Okay, they can be equal to at points, but g is always greater than or equal to f of x, and always less than or equal to h. So this would be a picture of that kind of a scenario. Here's h, here's f, and g is in between it all the time. Okay. So for an x near some a, except possibly at a, so I don't really care what happens at a, and I know that the limit of f of x as x approaches a equals the limit of h of x as x approaches a, and that has a limit, then I know that g has the same limit. So it is forcing g to have the exact same limit at a as the other two functions. This is what the squeeze theorem does. So for some expressions that you cannot do any of the techniques I've talked about, sometimes you might be able to do an expression this way. So let's look at an example that requires us to do the squeeze technique or sandwich theorem. So here's an example right here. All right, I have a product function, so right here. So we have some properties that we might be able to use. But I noticed right off the bat that I cannot do direct substitution because that's a 0 in the bottom of a fraction. You can't have that. Okay, so I already know that I can't use the properties, the product rules and stuff like that because of that issue. Okay, that doesn't mean the limit's not going to exist. It just means I can't use those properties because of that. So I have to do something different. So we have to start thinking things through. This one is not. This is not a problem. This is the problem function. But it's a cosine function. So the way you kind of like look at these things, and you say, okay, the cosine function. If you think about what the graph looks like, it is bounded. Okay, it does not go up to infinity. The x's, the y's don't go to infinity. They are limited and stuck between -1 and 1. The cosine function, it doesn't matter what this looks like in here. The cosine of anything is between -1 and 1. Think about your unit circle. Okay, this is true for all x that are not equal to 0. Okay, well, that's not my function, but I can build my function by simply multiplying everything by x squared. So that means now I know that x squared times -1 is less than or equal to x squared times the cosine of 1 over x, which is less than or equal to x squared times 1. And so I have now found my function permanently between two other functions. I know that the limit as x approaches 0 of a negative x squared, this side, is going to equal, actually, let's do it this way, is less than or equal to the limit as x approaches 0 of this function, which is less than or equal to the limit as h approaches 0 of this function. The limit of this function is 0. I can do direct substitution here, so if I plug in 0, I'm going to get 0. And if I do direct substitution here, I'm going to get 0. So what does that tell me? So this limit is sandwiched between the limits of 0. So now I know that my answer has a limit at 0. Okay? That's how the squeeze theorem works in that scenario. You can build a function. You build your function up by having something that you know that is indeed bounded by two values, and then you can build your function out and do it this way. Okay? Here's another example down here. Kind of twist on the same thing. And so what kind of clue makes me see this is I'm looking for a limit, and I gave you this information like this. So they're kind of building this up. So you got to learn to recognize what's going on here. So they gave me the two functions. I know all this information here. Here's g, here's h. F satisfies this condition, which was the condition of the squeeze theorem. So what is this answer? Okay. Well, to do that, let's find the limit of this function as x approaches 1. So what is the limit as x approaches 1 of g of x? So what is that going to be? We can simply do that very easily. And we can put in what g is, which is a -2x squared plus 4x plus 1. There's the function. We can do direct substitution. -2 times 1 squared, 4 times 1 plus 1, and we get the number, it looks like, of 3. Okay? Now we do the same thing for the h of x. So that'll be the limit as x approaches 1 of h, which is 1/2 x squared minus x plus 11 over, that's not a 5, 11 over 2. Okay? And we can again do direct substitution on this one. So 1/2, 1 squared, minus 1, plus 11 over 2. And you'll notice that you're going to get a 5. That was interesting. But wasn't one of our conditions the fact that the limits of these two things had to be the same? Right? The squeeze theorem works if I have this condition, which they gave me, and this condition has to be true. And it just shown that that it fails in this example. Okay? So then you can say, this is how you would write. So because the limit as x approaches 1 of g of x does not equal the limit as x approaches 1 of h of x, there is not enough information to determine the limit as x approaches 1 of f of x at this time. Okay? That does not mean I can't find the limit of this thing. I just can't find the limit using the techniques that I have been giving you at this time. Okay? So, as you'll see here, I said that down here in these notes too, so you can kind of take a look at this and pause it here just a bit more, so hopefully you guys can pause it and zoom in. And you'll notice I said right here, the inability to use the squeeze theorem does not mean the limit does not exist. It just means you couldn't figure it out using the techniques you currently have. Okay? So this is very important to remember this, that just because you can't find the limit doesn't mean it doesn't exist. Okay? It just means that using the current techniques you have, you do not know how to find the limit of that. Okay? So that's going to conclude this video right now. There's another technique, but that will be coming later. Okay?